Hello everyone, welcome back to Calc 3. We're going to pick up where we left off, talking about section 14.5. I'm going to start with talking about geometric interpretation of directional derivatives. So this surface that we see here is from the example that we did in the last video, what we finished up with. This is the surface 4 minus x squared minus 1/4 y squared. And this red point here is the point where we want to take the directional derivative. So what a directional derivative tells you is how the function is changing. In this case, the function value is the z value, the z coordinate of these points. So directional derivative tells you how this surface is changing in the z direction, so how it's changing vertically. So if we take a directional derivative, you can imagine that you're standing at this point, you look in the direction of the directional derivative you want to take, and that number tells you how the surface is changing vertically. So if I take a directional derivative this way, let's say, that derivative should be positive. If I am going somewhere along this direction, that directional derivative should be negative. If I go these ways, that directional derivative should be 0, because my z coordinate isn't changing at all. So now if we go through the example that we did, here I've just computed the directional derivative. That was the answer we saw before, -1 minus square root of 3/2. And now I'm actually plotting a line going in that direction with the slope of the directional derivative. So the directional derivative is the z component of the direction vector for this line. And so you can see we got a negative number, -1 minus square root of 3/2. So this line, we're traveling in this direction. We're going down. Now, if you remember from the problem, you can also go back and look. It said that the direction we wanted to go made an angle of pi/3 with the positive x-axis. So that might be hard to tell from this point of view. All we see is the tangent line there. It is tangent to that surface. But if I look from straight above, here's the positive x-axis. Here's the tangent line looking straight above. It does make an angle of pi/3 or 60 degrees with the positive x-axis, or at least it looks like it. So that is indeed the direction we wanted to go. So now that's the end of that example. Let's switch back to notes. Let's do another example of calculating directional derivatives. So in this example, our function, still a function of two variables, is going to be x squared sine of 2y. And we want to find the directional derivative at the point 1, pi/2, and the direction of 3i minus 4j. Now immediately here we have a problem. We need to make sure our direction is a unit vector. Here our direction is 3i minus 4j. That is not a unit vector. So we have to find a vector parallel to this one that is a unit vector. We did this back in chapter 12. All we have to do is find the magnitude of v. And here it is here. We square the components of v, add them together, take a square root. If we work it out, we get 5. And then we divide v by its magnitude. That gives us a unit vector. So our direction vector u is going to be v divided by its magnitude, 3/5, -4/5. And now this is a unit vector going in the direction where we want to take our derivative. From here, it's exactly like the other example. We're going to calculate the gradient. So I go to this function, x squared sine of 2y. I take a partial derivative with respect to x. I get 2x sine 2y. I take a partial derivative with respect to y. I get cosine 2y times 2. I need to use the chain rule, and I get a 2x squared cosine 2y. You may be asking yourself at this point, why am I allowed to use the chain rule I learned in Calc 2? Why don't I have to use the chain rule we learned the other week here? Well, the reason is, if we look up here, and I want to take a derivative here with respect to y, I'm really concentrating on this sine function. The outer function is sine, the inner function is 2y. So if I think of this 2y, let's call that u. U equals 2y. If I want to take the derivative of u is a function of one variable. And so here, if I take the derivative of u, I can just take an ordinary derivative. And I can use the Calc 1 chain rule. If, however, I had u was a function of two variables, u was a function of x and a function of y, then I would have to use the chain rule that we learned the other week. So this is the simpler case, where we can just use the good old chain rule, not the new chain rule. Okay, moving on. So we've calculated our gradient. Now I want to plug in the point 1 pi over 2. So 1 gets plugged in for x, so whenever there's an x, I plug in a 1. Wherever there's a y, I plug in pi over 2. And I finished calculating this, and the gradient evaluated at that point is 0 and negative 2. And from here I just calculate a dot product. Now this is nice because 3/5 gets multiplied by 0, that just drops out. And all I'm really doing is multiplying negative 4/5 times negative 2, and the answer is 8/5. So that means if I were standing on this surface, x squared sine of 2y, and I was standing at the point 1 pi over 2, and I looked in the direction 3/5, negative 4/5, the surface would be rising at a slope of 8/5. That's our directional derivative. So now let's talk about some more properties of gradients and directional derivatives. If I'm standing on a surface, can I figure out which direction the surface is increasing the most? How much it's increasing and which direction I would have to go? And yes, we can. And this is summarized in this theorem. So if we have a differentiable multivariable function, the maximum value of the directional derivative. So the directional derivative has a maximum value, and it's the magnitude of the gradient. And which direction do I need to go in order to get that maximum value of the directional derivative? I need to go when the direction vector is going the same direction as the gradient. Remember, the gradient's a vector. So I can find a unit vector going the same direction as the gradient. And that's going to give me the maximum value of my directional derivative. Now, why is this the case? First, let's think about why the magnitude of the gradient is the maximum. Remember, the directional derivative is defined as a dot product of the gradient dotted with a direction u. From our properties of dot products, we have this formula that's equal to the magnitude of the gradient times the magnitude of u times cosine theta, where theta is the angle between u and the gradient of f. Well, the magnitude of u is always going to be 1, because we make sure that u is a unit vector. So this directional derivative is really equal to the magnitude of the gradient times the cosine of the angle it makes with whatever direction we're taking. And we know cosine takes values between negative 1 and 1. So the largest that cosine can be is 1. So the largest our directional derivative can be is the gradient of f. Every other value is just some fraction of the magnitude of the gradient of f. The least it can be is the negative magnitude of the gradient of f, and that's going in the opposite direction as the gradient. So that's why the largest value is the magnitude. Why is the direction the same as the gradient? Well, one easy reason, right, is when do we get cosine equal to 1? When we take theta equal to 0. So that means the angle between u and the gradient is 0. They're going the same direction. That also tells you that we get the smallest value when u is going the opposite direction as the gradient, because cosine is equal to negative 1 when theta equals pi, when it's 180 degrees. But another way to think of this is that, as we said in the last video, the gradient is, or the directional derivative is really just a scalar component of the gradient in a certain direction, right? You can think of this as a scalar projection. So I'm projecting pieces of the gradient in certain directions. So when am I going to get the entire gradient? When I project it in the same direction as the gradient. So any other direction, I'm getting a piece of the gradient, a piece of the magnitude of the gradient. When I go the same direction as the gradient, I get the entire thing. And so that's why that works. Okay, enough about why these things work. Let's do an example. So here, I have a function of two variables, x e to the y. I want to find the rate of change when I'm at the point 2, 0, and I'm moving toward the point 1/2, 2. Well, we have a problem here. The first problem is I'm given 2 points. I don't have a direction. I'm told I'm standing at one point, or I'm placed at one point moving towards another point. So we can find a direction by finding the vector when we move from P to Q. So if I find the vector PQ, that's the coordinates of Q minus the coordinates of P, so that's pretty easy to do. I get the vector -3/2, 2. So this is the direction I want to go, but now I have another problem. Is this a unit vector? Remember, we always need to make sure that these direction vectors are unit vectors. So if I take the magnitude of PQ, I square the components, I add them together, I take a square root, I get the magnitude is 5/2. So no, this is not a unit vector. So I need to divide PQ by its magnitude, just like we did in the last example. So dividing by a fraction is the same as multiplying by its reciprocal. So I'm going to multiply PQ by 2/5, and I get that my direction vector is -3/5, 4/5. Okay, so that's the direction I want to go. Now I need to evaluate the gradient and make the dot product. So I'm going to go ahead and get rid of this because I've summarized the problem at the top of the next page. Here's my function of two variables. Here's the direction I want to go. Here's the point where I'm taking my directional derivative. So now I compute the gradient. Partial derivative with respect to x is e to the y. Partial derivative with respect to y is x e to the y. Nothing changes. Now I plug in the point 2, 0. And my gradient evaluated at the point is 1, 2. And then I can perform the dot product. So I dot 1, 2 with -3/5, 4/5. And I just get 1. So the directional derivative of f in the direction of u, which was -3/5, 4/5, evaluated at the point 2, 0, is 1. That's our answer. Now I have a follow-up question. In what direction is f changing the fastest? It says if, but I think it's supposed to say is. Go ahead and change that. In what direction is f changing the fastest at the same point, and what is the rate it's changing? So we just saw that the rate that f is changing the fastest is the magnitude of the gradient. The direction so the rate is the magnitude of the gradient, and the direction is a unit vector going the same direction as the gradient. So, that's what I've written here. We know the direction should be the same as the gradient, but a unit vector. So we've already computed the gradient at that point, 1, 2. Let's just make it a unit vector. So I compute the magnitude of that gradient, which is the square root of 5. So the direction in which f is changing the fastest at the point 2, 0 is this direction, 1 over root 5, 2 over root 5. Now, what is the actual rate that it's changing? Well, we've already found it. The rate that it's changing the fastest is the magnitude of the gradient. So we have our second answer with no extra work. So if you have a differentiable function and you want to know which direction you have to go for it to be changing the fastest, it's the direction that's going the same way as the gradient, and the rate that it's changing is the magnitude of the gradient. If you want the direction that it's decreasing the fastest, you just go the opposite direction. So you find the gradient, make it a unit vector, multiply by -1. That's the direction that it's decreasing the fastest. And then the rate it's decreasing the fastest, just put a negative in front of that number. So if I had this same function, the same problem at the same point, and I said, what direction is f decreasing the fastest? It would be -1 over root 5, -2 over root 5. And what's the rate it's decreasing? -root 5. That would be the answer. Okay, so we'll finish up this video with that example, and in the next video, hopefully we'll finish section 14.5, and we'll talk about how the gradient vector interacts with level curves and level surfaces, and we'll start talking about tangent planes and things of that nature. All right, see you soon.